Welcome everyone. This is the second derivation of the Euler Lagrange equations. This one is going to be a bit more formal, and this is the presentation that's usually given to undergrad physics students. So I like this one more, but the last one is actually my favorite just because I really like math, and that one is the sort of mathematically correct way to do things. Okay, so our situation here is that we have some particle. We describe its trajectory in a position, velocity, whatever, through these generalized coordinates. And then, based on the sort of physical setup, we have a Lagrangian for the system. We integrate that to get the action. And then our sort of fundamental physical principle is that the action must be stationary with respect to variations of the trajectory. And what that then implies is the Euler Lagrange equations. So in the last video, I used these QIs in these sort of approximate methods to denote the Q. It was a one-dimensional system, so we just had one Q. Could have thought of it as X. And then QI was Q at a time Ti. So that's different from what the rest of the videos have been about, where QI is labeling a sort of degree of freedom. So that is the QI that we're going to return to today. And we're focusing really on one particle. It's a bit easier to consider, but the derivation I'm going to do in this video does not depend on how many particles there are. So just for visualizing, we're going to think of one particle. So what's happening is that at our initial time that we call A, we know the particle is at this position Q0. And at the final time, B, the position is at this, the particle is at this position QF. Okay? So this 0 and F are just denoting that this is the initial position, this is the final position. Then suppose that the particle follows this kind of trajectory due to the laws of physics, that this is the physical trajectory. Then what we mean by saying that there is a variation to the trajectory is that at all times in this time interval, we could consider a sort of new trajectory that varies from the original trajectory by only an infinitesimal amount at each time. Okay? So we kind of have these new positions, Qi prime of t. I want to emphasize that the prime does not mean a derivative, the prime just means it's the new one. And that this is equal to, let's see if I can do this. Like black pen, red pen, like that, but I don't think I can do it. This is equal to the original Qi of t plus some variation or perturbation that we're going to call delta Qi of t. Okay? So between these two trajectories is this delta Qi, or these delta Q's. Okay. So there's one condition that we want to impose on this, which is that we know what the initial and final positions are, and we don't want to change them when we do this variation. So what we must have then is that delta Qi of our initial time, A, is equal to delta Qi at our final time, which is equal to 0. So when these are equal to 0, that means we're not changing the original trajectory at those times, right? So we see that both the original and the varied trajectory start and end in the same place. Okay? This is actually very important. So, right, what? Okay. Right. Then this principle of stationary action, or least action, whatever you want, is saying that any such variation of the physical trajectory q will induce no variation in the action. So how does that actually work? Well, we could look at the variation of the action. Let's do it here. So this delta S is equal to, so S when we put in these sort of q primes. So let's just put an I here, but we know that we have one for each I, each degree of freedom. And then we're going to subtract the original action. And then you can just plug in and see what this becomes. So they're both going to be an integral from a to b. Let me make this a bit more visible. So the first one, we have the Lagrangian where we put in the q primes. So qi prime dot. And then could depend on time. And then we're going to subtract this integral. I'm just going to get rid of the t's for now. So I could just write this as this. So if qi prime qi dot prime t dt. So this is the new action minus the old action, and that gives us our variation in the action. Okay. Now, we know that the new trajectory, the varied one, differs from the physical trajectory by only an infinitesimal amount, right? So we could then treat this new Lagrangian, or the new value of the Lagrangian, in such a way. So the new value of the Lagrangian, we're essentially going to Taylor expand this. So yeah, actually, so let me just isolate this term. Well, we can substitute in our expression for the new trajectories. So this is qi plus delta qi. This is qi dot plus delta qi dot. So this delta qi dot is just the time derivative of delta qi. You can just see that straight away from differentiating this equation with respect to time. Okay, then we have t. And then Taylor expanding, or really, you can just think about this whole thing as using the multivariable chain rule. The whole point is that we're saying that, the whole point of this derivation is saying that we've introduced a, tiny infinitesimal change to the trajectory. What is the induced change in the Lagrangian? And therefore, what is the induced change in the action? Well, the induced change in the Lagrangian, so first we'll start off with your original Lagrangian. But the induced change, well, we've changed the Lagrangian by changing the position, right? So the induced change in the Lagrangian because of that would be dl by dqi, and then times the delta qi, right? So this is all at a specific time. So this is basically like saying if we change the x coordinate a bit, then our induced change would be dl by dx times the delta x. So delta x is the change in x that we introduced. But since there are all of these different qi's, there's one for each degree of freedom, we have to sum over the i's. And yeah, I'll just put that in. There's a convention where you don't put the summation symbol in, it's just understood, but for now I'll just leave it in. Okay, so this whole thing is the change in the Lagrangian due to changing the position. But the Lagrangian also depends on the velocity, and we've also changed the velocity. So we get an additional change from changing the velocity. Sorry. Okay. And the way I've determined these is just from using the chain rule. Okay? But it should be sensible enough. And then if you're thinking about this as a Taylor expansion, you're probably like, well, what about the other terms? And the point is that these delta q's and delta q dots are so small that the other terms are essentially zero. But if you just think about this as from the chain rule perspective, then this is all you need. Okay. Well, for the variation in the action, we're integrating the difference between this and this. The difference between this and this is just this expression that we found. So the variation in the action is the integral of exactly this thing. So we're summing over I, and then we have this term. Okay, so integrate all this over time. And so all this should have been not so crazy. This is more intuitive math, where we're doing things just based on our sensibilities and maybe some intuition from calculus, which if you don't have intuition for calculus, then that's a bit unfortunate, but these are things that can be thought of more conceptually. But from here, it's more just trickery. So the point of what we're going to do is that we want to get this into a form where we're integrating something times these delta q's, and then we're going to insist that the variation in the action is zero, because that's what we mean by the action being stationary. And if this is zero, and it's zero regardless of what kind of variation we do, right? Because we're saying the action is stationary under any infinitesimal variation of q. Then the argument is that, well, if it doesn't matter exactly what this is, then that means this thing has to be zero. Okay? So that's the end goal. The trouble is right now that we do have something where we're sort of multiplying by delta qi, but here we don't. We have these delta q dots. Okay. But there is something that we can do about this. So remember that these delta qi dots were just the time derivatives of delta qi. Okay? So what we have in here is d by dt delta qi. Okay, this whole thing we're integrating over time. And just looking at this term, what we can do to convert this derivative into just this thing, because this is what we want to multiply by, is to use integration by parts. Because integration by parts will convert this derivative into the derivative of this, but we have to flip the sign. Okay? And then there are other terms that will come out from that. So it's the uv part will come out from like uv minus integral v du. But we're going to see what happens with that. So integrating by parts, and you can check to make sure that this is true. So we have this integral. Okay. So when we integrate by parts, we're going to have the two terms just by themselves come out and then be evaluated at the bounds. And then we're going to have minus the integral with respect to time of the, so we can, yeah, I'll just write it like this. So the derivative of dl by dqi dot, and this times delta qi. So all of this is integrated over time. And then what comes out at the end is this term dl by dqi dot times delta qi. And then this is evaluated at the bounds, and then we find the difference. Okay. If you're not super comfortable with that, then just pause and work this sort of thing out, the integration by parts. And we're integrating by parts for each I. Since for this term there are as many integrals being done as there are degrees of freedom. So we need to do it for each one of those degrees of freedom. Okay, so if you're comfortable with this now, then what we're going to do is look at this last part. So we often call these boundary terms. Hopefully it's clear why, because they're evaluated at the boundaries. And if you look closely, we're going to plug in b and a for the time t. But remember what we said, because we're fixing the initial and final positions, the variation of the trajectory at these times is 0. So for both of the boundary terms that we get into here, we're going to get 0 for all I, right? So I should have included that sum for I. or sum over I. But it doesn't matter because each of these terms is going to be 0. So actually, this whole thing vanishes. And what we're left with is just this. Okay? So hopefully this is getting closer to what we want. So let's go up here. Okay. Now, notice that we're multiplying by delta Q here, and we're multiplying by delta Q here. So now we can factor delta Q out. So what's going to happen is that we have this integral from a to b. We have a sum over I of dl by dqi minus d by dt of dl by dqi dot, then this times delta qi, and then we sum over I, and this integral is done over time. Okay. Well, this is always 0 because this is just the variation of the action, which we're saying must be 0. And if this is 0, for every infinitesimal variation, delta q, well then what must be 0 is this. And there's kind of one thing that I have to be a little careful about. This is a sum, and so we want to make sure that, so if there was no sum, if I got rid of the I, now think about it. It's a bit more clear that if this integral is 0, no matter what delta q is, then this has to be 0, because we could just always make delta q non-zero, right? And then say that, so make delta q non-zero for all t, and then this clearly has to be 0, right? Or maybe more clearly, we can make delta q always positive, and then this expression here has to be 0. When we introduce these sort of multiple degrees of freedom, it becomes a bit less clear. But the solution then is to just, for each I, choose a variation of the trajectory where all the other degrees of freedom were not varying, right? So if you're dealing with the first degree of freedom, choose a variation where you're not varying any of the other q's, and then we're just left with that one-dimensional case. And in the one-dimensional case, we know that each of these terms, for each I, has to be 0. So what we get from that is that this delta s equals 0 implies that for each degree of freedom, we have, we get this equation. And then just rearranging things, we can see that this is exactly the same as the Euler Lagrange equations. Okay. So this is still slightly informal, derivation of the Euler Lagrange equations, but it is much more correct and pretty much gets the idea right. So we've gotten a more precise idea of what it means for the action to be stationary, which is in terms of these sort of variation functions. And then what we didn't discuss is what exactly we mean by them being infinitesimal. But how you could kind of describe it is the variations are so small that this equality relating the new Lagrangian with the old Lagrangian, that this is true. Basically that the delta QI's are so small that we get no other terms. Okay? All right. So hopefully you guys are happy with this. And I'll make some other videos later talking about the more rigorous formalism that we need to introduce about what are called functionals, and then using that to derive the Euler Lagrange equations. All right.